Okay, we have one more quiz left. It's going to be over chapter 11, alcohols and ethers and those reactions. Okay, so make sure you are studying for that one on next Wednesday. Okay, the following Monday is our last exam, exam 3. Okay, so as of now, you have every reaction you need to know for the final. Okay, you should hopefully have around 50 of them on your reaction table. Okay, so, you know, there's variations of things, but it's around 50, 56, okay? So, and you should know your reactions forward and backwards. Okay, there's going to be multi-step synthesis questions on this last exam and the final. So I'm going to start going through some of that with my synthesis review and spectroscopy review. And we're talking about multi-step synthesis and how to read those. My favorite thing to do in a multi-step synthesis is to draw the product of each step to make sure you don't miss out on losing a carbon or adding a carbon. So anyway, so you need to know all of your reactions, and here's just a few of them. These are just some of the ones that you can use on an alkene. Okay, so and it's all things we know. You know, permanganate's going to clip it. Osmium's going to give us a diol. Metachloropurbenzoic acid is going to give us an epoxy. Hydrogenation is going to give us an alkane. Boron, borohydration, dehydration gives us the primary alcohol. Water would give us the tertiary alcohol. How would we get the secondary alcohol? Oh, with the mercury. And remember, on the mercury reaction and the water reaction, we can add alcohols and get ethers. We learned that in chapter 11. We added that on. It's the same reaction, except you add an alcohol instead of water, and you get that. NDS with peroxides, you get your product, the most substituted product there. But HBr and peroxides, you get the bromine on the less substituted side. And of course, HBO in the dark, you get your Markovnikov product right here. Bromine in the dark, you get addition, etc. So these are all just reactions that you can do with alkenes. But remember, we have lots of alcohol, things we can do with alcohols, including make ethers and break ethers, turn them back into alkyl halides, turn those alkyl halides into almost anything using an SN1, SN2 reaction. So make sure you know your reactions, okay? So we really only have a couple kinds of reactions. We have the radical halogenation reaction, and that can be NDS or bromine, right? And we have only two things it can do: abstract a hydrogen or add to a double bond to create another radical. Okay, and then it only has 3 steps: initiation, usually with a peroxide, propagation, and then termination. Okay, hopefully you got those right on quiz today. But then we also have SN1 and SN2. And of course, with that, you just need a nucleophile and a good leaving group. Okay, E1 and E2, you are looking for an elimination reaction. So you're looking for bases. Okay, and E1 and E2 is differentiated by the substrate and the type of base. So don't forget that. And then of course we had electrophilic addition. So we really don't have that many types of reactions. We have addition, substitution, elimination. Okay, and if you think about it, the halogen, the bromine and stuff in the halogenation chapter, those were all substitution reactions. We took a hydrogen off, put a bromine on, or put a chlorine on. Okay, so then we also have carbon-carbon bond forming things. This is how you can extend your carbon chain. You can use the acetylide ion as a nucleophile, or you can use the nitrile or the cyano ion as a nucleophile. Okay, but we have lots of other nucleophiles. We can make oxygen-carbon bonds. We can make oxygen-nitrogen bonds. These can make carbon-carbon bonds, halogens, sulfurs. And then, of course, we have our neutral ones here. These two being very poor nucleophiles. This being the worst nucleophile, this being better, and these being pretty good. Okay, so questions about the types of reactions we're doing. Okay. Technically, this carbon-carbon bond forming reaction is a substitution reaction, but I want to draw attention to it because when you're doing multi-step synthesis and you have a different number of carbons on the starting material that you have on your product, you must use some kind of carbon-carbon bond forming, or if it has fewer, you got to use something that oxidizes something off. So we got to pay attention to that. So I went over this before. We're looking at that retrosynthetic steps. We want to see how many carbons are on each end and see if we need to add carbons or not. We don't need to add carbons, then we just have to worry about making the right, turning it into an alkene or putting the halogen in the right place or putting the oxygen in the right place.
Is this in the
Yeah, this was in chapter 7.
like this whole slide?
Oh, no, this is, yeah, should be in there under files or under resources. Oh, I might not have published it. No, I think I did.
What is it called?
It's called, this one's called Synthesis and Spectroscopy Review.
So I kind of noticed on chapter 10, because they were doing multi-step problems on there, and I was kind of struggling to figure that out. It seemed like a lot of times they would make an alkene first, because that gave you a lot more options to be able to make things. Is that pretty common?
It can be, it depends on the thing. We're going to go through several examples today. And so maybe you'll see that, maybe that is a trend, I don't know. But we'll find out. Okay, let's go ahead and publish that. All right. Organic chem. Resources. Here, I'm going to preparation for the exam is published. Oh, interesting. So I'll have to publish that. Sorry, I thought I had it in there. Oops. I'll put it up as soon as I get out, but we'll have to just write down the practice problems. Okay. So now we want to, after we figure out that we have the right number of carbons and we don't need to add any carbons or take away any carbons, because to take away carbons, we have to do oxidation of an alkene. We have to look at what the functional group is that we're trying to get, okay? And know a couple of reactions that can get to each of those functional groups so that you can back up and from there. And then you work backwards. You said, okay, well, if I ended up with an alcohol, I could have started with this, this, or this. So those are possible reactions, but what could I do with the starting material to make that intermediate? And then once you choose the 2 reactions or 3 reactions that can do that, then we have a good way to work forward. Then you just do it all forward. So the starting material, you convert it to this functional group, and then you know a reaction that converts that functional group to the functional group that you have. Okay, so let's start with something simple.
You can't see.
Oh. Okay. It's funny, I can't grab it because it's, there we go. There. All right, let's start with something simple. Okay, how are we going to make acetylene from ethane? Okay, hydrocarbons only do 1 reaction. Well, until chapter 10, hydrocarbons only did 1 reaction. So what do you think we might want to do here to make it into acetylene? Okay, so let's think about some of the reactions we know that we can make, how to make acetylene. So how can we make acetylene? Well, we can make it from a alkene with an alkyl halide on it. Right, and then we can make that from an alkene with 2 alkyl halides on it. Okay, what would be the reaction conditions for making the alkene with an alkyl halide on there? It's an elimination reaction, a non-nucleophilic base. So something like T-butoxide. But can we use T-butoxide to make acetylene? No, we have to use sodium amide. Sodium amide, NH2. That's the only base, huh?
It has to be a strong base.
Making an alkene, yes. But to make an alkyne, you have to use sodium amide. To make an alkyne, you have to use sodium amide. Okay, so that means we could use the same sodium amide here and just use 2 equivalents because that same base will work for that, okay? So how do we get to this dibromo compound from here? How do we back up to there? Okay. Well, we could go a really long way and brominate it using radical halogenation and then eliminate, giving us an alkene, then put bromine on it. Or we could do 2 equivalents of bromine with a radical halogenation, so peroxides, ROOR, right here. So now we have, that's going to put 2 bromines on. It's going to put bromine on one side, a bromine on the other side. Okay, so let's do it forward now. Let's take all this away and figure out what we're going to do. Okay, remembering all those reagents we just used, we're going to first do reaction with 2 equivalents of bromine, Br2, with peroxides. Will generate Br, H, H, Br, H, H. Okay. We substitute one side and then the other side. Okay. Then we're going to take that and use 2 equivalents, 2 equivalents of sodium amide. And that's going to make our acetylene here. Okay. See what the strategy was? Yes.
What is the arrow? Yes, what is that?
This is a reaction arrow. The double lined arrow is a retrosynthesis arrow. So, but we can't make it directly here. So we're going to make this one first, and then we're going to make this one second.
I'm just asking what does it say above the arrow? Sorry.
What does it say above the arrow? Oh,
Okay.
because my handwriting is not perfect. Okay, let's go 2 equivalents, EQ, Br2. And then 2 equivalents, NaA, oh, no, that's not right. NaNH2, sodium amide. So yeah, we have no new reagents. You have all of the tools you need in your toolkit now. We just got to sharpen them and figure out how to use some of them. Okay. So let's do this one right here. So this is another way to ask the question. You know, this could be where there is a 1 on front of this, then there's a 2 here, and there's a 3 here. Okay. So if you have a 1, a 2, and a 3, that means you do the reaction first, and then we figure out what that product was. Then you do the second reaction and figure out what that product was. Then you do the third reaction and figure out what that product was. So if we do this with sodium amide, that's a strong base, it's going to deprotonate that acetylene, okay? So what you're going to end up with is that with, we're still keeping our acetylene, we haven't lost it yet, and we're going to add to it this right here. So now we've made a nucleophile out of our acetylene, and so it's going to displace the bromine on the next reagent. So that's going to give us 1, 2, 3 carbons. So we got to do 1, 2, 3 carbons added to it. And then we're going to do reaction with hydrogen plus Lindlar's catalyst. What kind of alkene does Lindlar's catalyst give us? It's a syn addition. So what kind of alkene does it give us?
You mean what? Cis and trans?
Yes,
Cis.
cis. It gives us a cis alkene. Okay, so now let's look at our products here. This is a trans alkene. It's not going to be that. This is a cis alkene. And this is a cis alkene. But look where we have, this has got an isopropyl group on it. Okay, so because we have the Lindlar's catalyst, we know it's not going to go all the way down to the hydrocarbon because we only have 2 choices for cis alkenes, but one of them has the wrong group. One of them has the propyl group and the benzene. The other one has the benzene and the isopropyl group. So be careful. So, but we did it by doing each step independently and then looking for the product we wanted. Question on that?
I think I'm confused on like the first step of it.
Mhm.
Like NaH2. What does that really mean?
Okay, this is a strong base. It deprotonates the acetylene and makes the acetylene a nucleophile to make a carbon-carbon bond. So this is going to react with this in a nucleophilic fashion. It's going to do an SN1, XN2 reaction to displace the bromine. So we have a carbon-carbon bond between this carbon and that carbon, which gives us our product here.
Oh,
And then, now that we have that there, we're going to use Lindlar's catalyst to give us our cis alkene, and that gives us some choices on final products. Okay. Also, sometimes they're just written as words. Okay, so you need to translate it into an image to see what's happening. So don't be confused. You know, that's why I want you to know your reactions forward, backwards, and in the middle. Okay. All right. Now, let's see which of these two reaction sequences, which two of these reaction sequences will affect the following transformation. Okay. So we've started with an alkene. I'm sorry, an alkyne, and then we got a cis diol. Okay, I'm going to call that a cis diol because drawn the way it is, it looks like a cis diol. Okay, so let's see what would happen if we did hydrogen with nickel and boron. That's another reagent for Lindlar's catalyst, right? So we would get a cis alkene right here. And then we would use osmium, and that's going to give us a cis diol because the osmium is going to add a cross like that, and then we're going to take the osmium off. So that's going to give us a cis diol. So this one will give us our reaction that we want. Okay. There we go. Okay. So let's see what happens when we do this one. Sodium with liquid ammonia. What does that do? That's the reagent that gives us our trans alkene, right? So we're going to get a trans alkene. And if we added if we added osmium to that, that's going to go on the same side, right? And that's going to give us the enantiomer of this. It's going to give us the methyl groups are on opposite sides now. So this will not give us the product we want. Okay, see how to stack reactions together right there? Draw the intermediate. Yes.
So for that, the methyls would be trans, but the OHs would be cis.
So if well, let's say the OHs are going to be on the same side, and then the methyl groups would be trans to where the oxygens would be. So if we held in this position, this methyl group would be back here for this one, because we have to add the syn addition. And so we're going to keep the oxygens where they are and show you the methyl group is down the back. Okay. Because the hydrogen would be out toward us when we do that syn addition. And that means it's the wrong isomer. All right. So let's see what the next one is. Okay. So we have, let's see. Oh, that looks like Lindlar's catalyst again. So we're going to get a cis alkene.
I can identify that.
Well, because the two types of Lindlar's catalyst are called Lindlar's catalyst, or lead sulfate, or nickel to boron. Those are the three things that signify it's a cis alkene catalyst, or a poisoned catalyst. Okay, now look at this really closely. There's a 3 there, CO3H. So what's that?
Peroxide.
It's a per carboxylic acid, but it does one thing and one thing only. What do per carboxylic acids do? They make epoxies. Okay, so the next step here in this one right here is going to make us an epoxy right here. And then when we add water to that, it's going to go anti-addition on the bottom right here, giving us a diol. Now let's look at what that diol is. we have, let's see, the hydrogens are back. Hydrogens are back. OH is here. I mean, methyl group is here. So we're going to keep a methyl group here. We're going to put our OH down here and our hydrogen back. We're going to put our OH up here. Our hydrogen is back and our methyl group is forward. CH3, I'm going to erase the CH3. And when we rotate it so that the oxygens are on the same side, this methyl group is going to shift to the back. This methyl group is going to shift to the back. So when we have both oxygens in the same position, we have the wrong isomer. So that's no. Okay, but what if we do liquid ammonia? Okay, that's going to give us our transalkene. So that's going to give us our transalkene first. So we're going to get our transalkene with dash, 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 CH3 hydrogen out here. And then dash, 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 hydrogen, dash, and CH3. And when we do that same per acid, we're going to put an OH here. Okay. And now when we attack it with our nucleophile, right here, it's going to open up and give us CH3 in this direction, CH3, hash, 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 hydrogen, and OH, and dash, 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 CH3, dash, hydrogen, and OH. Now look what happens when we rotate that one. When we rotate that one, the methyl group that was in the back now rotates to the front, and it gives us the correct one. And so we can say that. All right. So this is why you look at that reaction table for selectivity. Selectivity. The anti-addition of the water on the epoxy gives you that selectivity and tells you where things are going to be. Okay. So let's see. Oh, and is this a chiral molecule? Just to double check.
Yes. Oh, no, it's
It's achiral because
It's got a place.
it's a meso compound. Yeah. Okay. So, all right. Are you getting the hang of multi-step synthesis? All right. Let's practice some more. Okay. So this is actually the same thing. All right. So there we go. How can we accomplish the following transformation? All right. So what was the first thing? Count your carbons. So let's count our carbons. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay. So we don't have to make any carbon. We don't have to add any new carbon-carbon bonds. Looks like we need to break a carbon-carbon bond. Luckily, we have reactions for that. But let's look at our functional groups now. Aldehyde, aldehyde. Ooh. That just down selected our number of things that we can use, right? So if we have that retrosynthetically, that means we had this right here, and we reacted it with, not permanganate. What's the other one we used? Not permanganate, but then it had a reducing or an oxidizing, a reducing workup. Mercury. That would take a double bond and turn it into an alcohol or an ether.
The ozone.
Ozonolysis. Ozonolysis. So we use ozone with Me2S as our reducing workup, because that'll give us our aldehyde. Okay. If we did permanganate, it would oxidize it down to carboxylic acids. Okay. So if we wanted the dicarboxylic acid, we could do it that way. But now we have to figure out how to make this. And how do we make that? Well, we have to do some kind of elimination reaction. So I'm thinking something with a halogen or water. We could do a halogen or water. Yeah, halogen, H2O. But which one's going to be easier to do? Well, do we have a reaction that takes an alkane and converts it to something useful other than combustion? we have to use the radical. We have to use the radical. We have an unfunctionalized carbon-hydrogen bond, so we have to use the radical system. So that's going to back us up to being our, and we probably want to use bromine, but why could we use chlorine on this?
All those carbons are the same.
All the carbons are the same. You're going to get one product. Okay, so you could use chlorine or bromine, but it has to be in the presence of peroxides. Okay, so now we know how to get there. Now let's do it forward. Okay. All right. So let's see. We're going to do, starting with that, we're going to do bromine with peroxide right here. That's going to give us our halogen on there. Then what do we do next? Dehydrohalogenation?
Do elimination, right?
Right. So we're going to do an E2 reaction. So we're going to probably, it's a secondary, so we'll probably be able to pull it off with ET3CO2OH with, we can use a smaller base on this one because it's a secondary O minus right here. And so that's going to give us our alkene. And then we're going to use ozone in step 1. And in step 2, we're going to use Me2S. Now, if you wanted the dicarboxylic acid, you would instead use permanganate in water.
And is that the one that's done cold or hot?
This one's done hot,
It's cold as the diol.
dihydroxylation. And oh, there's some base in here too. Okay. So I can ask you this exact same question, just both one of the other, and you can back it up and get to the right synthesis pattern. All right, any questions from home? Okay, all right, so let's do a review of spectroscopy now. Okay, so I wanted to review spectroscopy because, of course, we did IR so long ago. And so I wanted to give us a little bit of a heads up there. This is in chapter 2. And remember, I said this is the most important chart. And it's not actually appeared in chapter 2. My wife actually made this about 5 years ago. And so I really like this. And it tells you how to structure things. You have your things that can hydrogen bond, right? And they're all going to be in this high range. And they have different shapes, right? The OH is broad. The carboxylic acid is broad and covers the 3000 mark. And the nitrogen tells you how many hydrogens it has on it. If it has 0 hydrogens, there's no peaks up there. There's 1 hydrogen, there's 1 peak. If there's 2 hydrogens, there's 2 peaks. So that's great. Nothing else is in here but triple bonds. Okay? Every once in a while, there's an aldehyde peak shows up right here. The H on aldehyde, carbonyl, shows up right here at 2700. But then we have our double bonds and our single bonds. And remember, these 3 regions help us identify the types of bonds we have, which helps us identify the functional group. Okay, it doesn't tell us the functional group, it tells us what bonds the functional group has. And we can eliminate that. Questions on IR? Okay. So some questions are going to say, you do this reaction and it has a strong peak at 3100. And then what was, what is the product? And given some other information about this was the reaction about. So you can go backwards with spectroscopy or forwards with synthesis, but getting both pieces of information to work together is really what they're trying to get you to do. All right, questions?
So
Yes.
the OH was different if it was on just an alcohol as opposed to carboxylic acid.
Correct. Yeah, OH on an alcohol is above 3000 and broad. The alcohol, the OH on a carboxylic acid is actually bridges 3000 and is even broader. So in NMR spectroscopy, for proton NMR, you have four things, okay? Number of unique hydrogens, or number of signals, their intensity or integration, their shift, and then their splitting pattern, okay? Look at those common splitting patterns because it'll make it very fast for you to identify, oh, isopropyl group or an ethyl group or something like that. Those splitting patterns are very common, show up quite a bit. Carbon NMR, we eliminate our integration and our splitting, okay? We just look for number of unique carbons, and don't forget the carbonyl, and number of unique, number of the shift. And the relative shift for them are the same. The more electron density that is being pulled away from that nuclei, the further downfield it shifts. Okay. Okay. And again, we don't see splitting or integration in carbon NMR. Okay, in mass spectroscopy, the four most important things are the parent ion peak, which is the highest peak except for that little 1.5%, which counts for carbon 13. So it's the one that's not the highest, it's the one, it's not the M+1, it's the M. The base peak, which is the tallest peak, which everything is calibrated to, the relative abundance of the different fragments. The bigger the higher the abundance of the fragment, the more stable it is, the more likely it is that it can be made that way by cutting in a couple different places. And the fragmentation pattern, okay? So we also need to pay attention to our molecular ion peak when we see M+2s, because M+2s give us halogens. And if they're equal intensity, it's bromine, okay? Fluorine only has one isomer isotope, and iodine only has one isotope. It's spin it shows up on that spectrum. So if it's chlorine, it's 3 to 1. Okay, it's like 2 to 1. Yeah, 3 to 1. Okay, and then the nitrogen role. If you have an odd molecular ion peak, you have an odd number of nitrogens in your compound. Okay, so really, I just condensed 3 weeks down into 3 slides. So, but it is these are the important things to look for. Okay, so what we'll figure out is on this exam, all of them are multiple choice. So what you need to do is you need to come up with an argument to eliminate choices. Okay, say, oh, this would have a peak here. It's not there. I can eliminate that one. Okay, so know your zones that you can have it in there. So look for major absorbances. Don't worry about carbon-carbon bonds or carbon halogen bonds, the single bonds. Look for the double bonds, the triple bonds, the hydrogens, and that. In NMR, in carbon 13, it'll be asking you to pick a structure, and you eliminate it. First thing you do is you look for number of peaks in each of your compounds. That can usually eliminate one. Then you look for relative shift. Is there something high enough to be bonded to an oxygen? Is there not something high enough to be bonded to an oxygen? You can eliminate something. Then, to put the nail in the coffin, you use splitting, spin, splitting. Okay? Spin, splitting. And if your spin, splitting matches your relative shift, matches your that, and occasionally they'll give you integration, and that can help you too. Then you go and start figuring out where your number of hydrogens would be to see if that integration works as well. But for the most part, you can do it by number of peaks and then splitting. Okay. And then, usually number of peaks and splitting works well, but then shift usually it takes in some problems. Like when we had that problem in class where I had an ethyl group bound to a carbonyl versus an ethyl group bound to an oxygen. We eliminated one or the other because of the shift. The splitting pattern was the same, but we eliminated it because of shift. Okay. So in mass spec, you want to look for your molecular ion peak and make sure it's not odd. If it's odd, look for the compound with nitrogen in it. Okay. When you're looking at your mass spectroscopy, if you see two molecular ion peaks that are of the same height, you know you have bromine. If you see two peaks and one's about 1/3 the other one, and it's an M and an M+2, you know you have chlorine. Okay. Now, the other thing you can do to help you figure this out is subtract the biggest peak, your molecular ion peak, from your what's it called? The big one. The base peak. Yeah. You subtract those two and you see if that's a common number. Like 18 is OH, 15 is CH3, 14 is CH2, 47 is C3H6, 7. So you can look for those, you can just add them up in your head and figure that out. Okay, questions on that? Okay, so now you have a strategy for how to attack these problems. You're going to look for things that give evidence for what you are looking for. So let's look at this one right here. And we have a weird little splitting thing here. We have, let's see, 1 peak, 2 peaks, 3 peaks. Okay, remember the 1 at 1 is the reference. So you ignore that one. So let's start counting our peaks here. We have 1 peak, 2 peaks, 3 peaks. So that's a possibility. 1 peak, 2 peaks, 3 peaks, 4 peaks. Can that be one of our choices? Hey, we've already got a, 33% better shot at getting there the right answer. Okay. 1 peak, 2 peaks, 3 peaks. Ooh, symmetrical. So yeah, that's still there. That's still possible. 3 peaks, 3 peaks, 1, 2, 3 peaks. So that's really possible. All right. So now let's go to splitting first. Okay. So this is going to be a singlet. This is going to be a triplet, quartet, 4, and this is going to be 3. But okay, so that's what we have. All right. All right, so this is going to be a singlet. Oh, we went into that one already. All right, this is going to be a triplet, a quartet, and a singlet. That doesn't help us any. Okay, this one's going to be a singlet, a triplet, and a quartet. All right, we don't have an integration. So what are we going to have to do?
Thought you flipped the splitting on this one.
I did? Oh, you're right. 4 and 3. Thank you. All right, we're going to have to do it by shift then. Let's see if it's in this region right here, it's going to be something bonded to a carbonyl. If it's in this region right here, it's going to be something bonded to an oxygen. So that means we have 2 things that are bonded to oxygen. Okay, let's see if we have any of those here. Okay, bonded to an oxygen here, bonded to an oxygen here, but only bonded to carbonyl. No oxygens in this one. Oh, good, we can eliminate that one. There's no oxygens in that one. There's 1 oxygen here and 1 carbonyl, so probably not that one. Okay, uh-oh. We don't have it bonded to an oxygen. What happened? The splitting works. Wait, hold it. It's not bonded to just 1 carbonyl, it's bonded to 2 carbonyls. So it took it from here to here. We're being crafty.
You have like a list of like those like areas, kind of like the region thing that you did for the spectrum on one of the slides.
Not on one of these slides. It's in chapter 9 though.
For like the carbonyl things. I feel like
Yeah. There's a table for both the proton and carbon NMR. Visual, not tables. They're diagrams. Yes.
Is there a good way of telling splitting? Because I know, like, I was trying to do stuff on the homework, and I was like really not able to count how much it split.
If it's not, I mean, this is laid out fairly simply, so it was pretty obvious that this was a quartet right here, and this was a triplet. If it's not, there'll be a 3 or a 4 or something, or a Q. Sometimes it's a quartet above it. If it's not clear, it will be a sign. All right. Okay. See how to attack that. We eliminated one of our choices immediately. Then we had to start looking at shifts, and then we had an unexpected appearance, but we were able to justify it because we had two different carbonyls. It's going to take it from here just a little bit higher. Okay. Questions?
Where's that diagram?
That diagram is probably 5 to 10 pages inside the spectroscopy notes, the chapter 9. Yeah. Okay, all right. Now we have some splitting for us. Okay, so we have 4, 3, 3, 3. That's going to be hard. And of course, this is our reference here. So we have 1, 2, 3, 4 signals. So let's see. We have 1 signal, 2 signals, and then that. So that one can't be it. Yay. We're winning already. 1 signal, 2 signals, 3 signals, 4 signals. Ooh, that's fancy. Okay, 1 signal, 2 signals, 3 signals, 4 signals. 1 signal, 2 signal, 3 signal, 4 signals. All right, so we're down to
How come those two aren't in B?
B
How come the middle two CH2s aren't same signal?
because it's this carbon here is shifted because of the chlorine. So this carbon is not equal to that carbon.
Well, what about the two middle ones? Because they're both.
Right, but that's just it. This is bonded to this carbon. This carbon is not equal to this carbon.
Oh.
So this has 3 hydrogens on it. This has 2 hydrogens and the chlorine on it. Therefore, they are not equal. Even though they're bonded to the same thing, the other side of it's not equal.
That's what I was thinking.
Yes.
How are we able to cancel A?
Only 2. Oh, wait, hold it.
There's a chlorine, right?
There's a chlorine. We can't cancel A. And this is going to be 3, 4. All right. Can't cancel A. Glad you saw that. Probably should look at that on the test. Look at the things twice. You might make a mistake. The first time I took the ACS exam, I only missed 1 question. And so, well, no, that's not true. After I taught the course, after I taught the course once, I took the exam just to see how well I do. And I got 69 out of 70. And I had to go ask why I got the other one wrong. But now I know that rule really, really well. Anyway, so, okay. Anyway, okay, so we have that. So now we have splitting. Okay, this is going to give us a triplet and a quartet and a quartet and a triplet and a triplet. No, there's only 1 hydrogen here. That's going to be a doublet, and that's going to be a triplet. Ooh, because there's 2 chlorines on here. There's only 1 hydrogen here. This is only going to be split into a doublet.
Oh, so you can.
Okay, do we see that right here? There's only 1 hydrogen. And so this is going to be a doublet. This is going to be 2, and this is going to be 3. Okay, now we can eliminate it. All right, now I'm lucky that that wasn't the right answer. Okay, so now let's look at this one. We have, this one's going to be a triplet and a triplet, quartet and a triplet. That didn't help. Okay. Let's do C. Let's see. A triplet and a triplet and a quartet and a triplet. Okay. And a triplet and a triplet and a quartet and a triplet. Okay, so we got 3 choices. So now we got to look at shift. Okay. So shift we have 2 things way above 4. We have 1 thing around 3. And then we have 1 thing around 2. So this has got to be the methyl group at the end, right? So we have to look at that. Oh, this looks like it probably, it's just below 3. So that has to be something with a halogen on it. Okay, so that's going to be something with a halogen on it. And then it looks like these 2 are going to be something next to an oxygen. Okay. So let's see which one can do that. Let's see. These 2 are next to oxygens. This one's next to a chlorine. So we'll have a quartet, quartet and, oh, we've eliminated that one. Sorry. All right. So this one is going to be higher than this one. So we're going to do, this is going to be highest at 1, followed by 2, 3, and 4. So quartet, triplet, triplet, triplet. That doesn't help. All right, let's go to this one. This is going to be, oh, there's no oxygen here. We can eliminate this one because there's no oxygen. There's only the carbonyl. What? Okay. So now we got this choice. We got the CH2 and CH3 on an oxygen, and the CH2, CH3 on a carbonyl. So now we have to look for that position of the quartet. The position of the quartet is above 3. The quartet has to be associated with a CH2 next to an oxygen. So that eliminates this one. The correct answer. Okay. Use the evidence you have. And read the question twice. So, all right. So let's look at this as a carbon NMR spectrum. So we're going to do number of peaks 1, 2, 3, 4, 5, 6, 7. Okay. Why are there D's and S's and triplets and quartets on there? I don't know, but we don't need to. So we have 1, 2, 3, 4, 5, 6, 7. Okay. So we have 7 peaks. So that's good. But we have 4 peaks in the same region. What region is that? It's the benzene ring region. So that means we have a benzene substituted in a way such that it has 4 different peaks. Okay, so that could be like an unsymmetrically substituted benzene. Well, no, that didn't help because we have unsymmetrically substituted benzenes. Okay, all right, what's this peak up here? Above 185. It's carbon NMR. Above 185 has to be a carbonyl. Okay, and it can't be an ester, it can't be a carboxylic acid, and it can't be an amide. Okay, because those would be between 165 and 185. So it has to be, so it can't be that one. It could be that one. It could be that one. And it could be that one. Okay. So we eliminated one of them just by that peak. And then we have one here at 40 and one here at 20. And I think this is saying the proton NMR says this is a quartet, and that is a, I'm sorry, this is a triplet and that's a quartet. So now we have to look at this and say, okay, how many different signals should we have here? We're going to have 1, 2, 3, 4, 5, 6, 7 signals. 1, 2, 3, 4, 5, 6, 7 signals. 1, 2, 3, 4, 5, nope, counted wrong. 1, 2, 3, 4, 5, 6, 7 signals. 1, 2, 3, 4, 5, 6, 7 signals. So signals doesn't help us. Okay.
Wait, you're not counting the bottom signal on C?
On C, well, because these two are equivalent.
Oh, okay.
Yeah. These two would be equivalent and those two would be equivalent. Okay. Just and so all of them, because they're unsymmetrically substituted. All right. So now, okay, let's figure out where we're going to go from here. Okay, now we'll have to do shifts. Okay, so where would a CH2 on a nitrogen be? And versus a, oh, wait, hold it. Let's look at this splitting pattern here, the triplet quartet. Okay, that's going to help us because that's going to eliminate this one. So we've already eliminated that one because the carboxylic acid. We're eliminating this one because we would have right here a doublet and a singlet, and this would be a singlet. So we can eliminate that one because the triplet quartet here of the proton NMR, they're giving us a little extra information here, is telling us that we can't do that. So now we have these two, this one and this one, okay? So now we have, this can be there, and we have this. So now we have to look at shifts. What are our shifts being right here and right here? The nitrogen carbon, the nitrogen bonded to carbon shift is going to be close to where ethers are. Where are ethers? They're a little bit higher, 60 to 70. So I think that's going to eliminate this one. And I think we're going to end up with this one. So we're getting this one eliminated because of the splitting pattern on the proton NMR. We're eliminating this one because of the position of the carbonyl. We're eliminating this one because we don't have the carbon bonded to a nitrogen shift. We do have a carbon bonded to a carbonyl shift. So, all right, we see how to attack these problems.
I'm still seeing the nitrogen.
So most of them don't use this right here. So I think that the new problems don't do this. So this is an old problem from the old study guide. So you shouldn't have that kind of issue. All right. Which compound would give you a molecular ion peak of 144 and a major fragment of 71? Okay, well, let's see, 47, let's see, 15 is methyl group plus 14 plus 14 plus 14 is going to give us what, 12, 17, 57. So that's 20 something away from that. So 57 plus a methyl, another 14 is going to give us 61. And another 14 is going to give us 75, maybe. So that means we probably have a carbon without an oxygen on it. Okay.
I should do that.
Okay, well, what I'm doing is I'm just trying to figure out what this ion is by adding CH3, CH2, 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 CH2 together, so we have the right peak. I think I did my math wrong because it should have come out to 71. Let's see.
57 is 14.
Would be 71. Okay, it is 71. Yay, 71. Good. So that means we have 1, 2, 3, 4, 5. So that means we have this as a fragment right here. 1, 2, 3, 4, 5. So now we have to find which of those structures can give us that fragment. Okay. 1, 2, 3, 4, and the carbon would be 5. 1, 2, 3, 4, 5. 1, 2, 3. It would probably break here or here. So it'd probably break there, giving us 4. So this one's going to give us a fragment of 3 and 3. This is going to give us a fragment of 3 and 2. This is going to give us a fragment of 2 and 4, which means it's probably going to be this top one. And it has a molecular ion peak that's even, so we know it doesn't have nitrogen in it. Okay, those were in the homework problems, by the way. We discussed that slightly. But, okay, so let's look at this. And okay, we have identified the spectrum to each of these. Okay, so now we're looking for where things are going to break. Okay, so let's pull up the first one here. It has a molecular ion peak of 73, and it has a fragment here at 30. Okay, so right away, we know exactly which compound this is because molecular ion peak is 73. 3 is odd, has to have a nitrogen in it, an odd number of nitrogens in it. We only have one that has a nitrogen in it. Boom, this is B. Okay, so use what you have. Okay, let's look at this right here. Our molecular ion peak plus a molecular ion peak plus 2. And they're of equal height. You know exactly which compound this is, right? It's bromine. So that's going to be D. And this one is 1/3 the height of that one. It's an M plus 2 peak. So that means it's the one with chlorine. C. And then this one is, let's see, we lose 15 here. We lose a fragment that is going to be, let's see, that's 2 carbons lost. So it's going to give us a fragment with 3 carbons. So that means if it breaks here or here, it's going to give us a 3 carbon fragment, which means that one is A. So, okay. So don't get too bogged down in the details. Use your 3 rules for those M+1, M+2s, and then look at your fragmentation patterns. Okay, questions on that? Okay, so let's see. We want to deduce the compound from all of the different information they gave us. Okay, so the first thing we have is we have a splitting pattern. We have something way up here. Okay, so I think that something way up there is going to be an alkene of some sort. And so we have a hydrogen there, 1 hydrogen, and it's a triplet. Triplet, triplet. This is a quartet or multiplet. And this is a singlet, one here. All right, and look what they did. On the carbon NMR, they showed you how many hydrogens are in each of these carbons. We have a CH3, a CH2, and a CH2, plus a C and a CH. Notice where they are. This is probably where our alkene is. And then we have a C way above our OH. So that means from here, we have a carbonyl. We have an alkene with only 1 hydrogen on it. And then we have maybe a couple fragments down here. Now, it looks like we have 3 hydrogens that have a singlet. So that means we have a CH3 by itself. So maybe we'll put that there. And then we have those which are forming the perfect ethyl group right there. And then, of course, we have our alkene over here. This only has 1 hydrogen on it. All right, let's see what the IR tells us. Okay. The IR tells us we have carbon-carbon double bond and an OH. I mean, sorry, a carbonyl, but no OH. Okay, so by looking at that, what are our choices? Oh, we're just figuring it out. Okay, yeah, we're just figuring it out. So our fragments include an alkene with a that was, we don't have there, so I don't know. Let's see, this is going to be hard without choices. We get choices on the exam, but I'm going to say we have, let's see, no, we have a C. Oh, no, we can have that. Then we can have an ethyl group here, a hydrogen here, and then we have a carbonyl somewhere here. So
And one of them was like a benzene ring. I was like, I had no idea.
yeah, this isn't a benzene ring. It definitely has a carbonyl. It doesn't, oh, it might have an aldehyde. There's a little thing there. Wow, this is a hard one. This is a homework from the last edition. So, okay, so, but the strategy is still the same. Find out what you can about it and then compare it to your choices. You will have 4 choices. Try to eliminate 1 or more of them. Okay. All right, so here we're going to do the same thing. We have a hydrogen way up here. So that could be only a couple things. That's usually an aldehyde. We have this peak here. That's usually a benzene ring. We have a multiplet, and we have 6 hydrogens and 1 in a double. That's a classic pattern. That's an isopropyl pattern. There's the hydrogens here, and then we have 3 over here and 3 over here. So this right here telling us we have an isopropyl on there. So we should be able to pick out something that looks something like that. Let's see if that agrees with our system, with the carbon NMR. We have 1, 2, 3, 4, 5, 6, 7 carbons. 1, 2, 3, 4, 5, 6, 7 carbons. This carbon has a hydrogen on it, which tells us we do have an aldehyde. Yay, so that worked out. These are all benzenes. There's only 2 of them have hydrogens on them, so it's probably these sets. These 2 are probably the ones here. And then we have 2 other types of carbons. This one only has 1 hydrogen on it. This one has 3 hydrogens on it. So yeah, it's going to be that para-substituted, that 1,4 substituted benzene. And we do have some peaks above. We do have some peaks above 3,000. So these are our aromatic ones. We have our carbon-carbon double bonds and our carbon double bond. And this big peak here at 2750 is our aldehyde peak. And then everything else is below 1500. So that supports our premise as well. Okay, so this gets a little harder as we go. And thank you so much. And we will start the full review on Monday.
That's what you're gonna do it in class.
This I was going to do in class. No, activity.
Oh.
Sorry. All right. Thank you very much. Don't forget to take your quiz. Okay, I'm going to stop sharing. And I'm going to stop recording.